All right, welcome back, everybody. So today we're gonna do the paper presentations. If you remember, we talked about trusted execution environments and remote attestation. So this week's presentation is going to be about those. The first paper will be about control flow attestation. Then we're gonna also talk about various different types of keys. After that, I'm gonna talk a little bit about the logistics for your exam next week. And also we're gonna talk a little bit about those small remaining things and also like the plan for next week. Okay. Before we get started, any questions? We're good? All right. So yeah, Mark is here. So whoever speaks just stays here. Other things stay whatever. You can actually move this a little bit to the right. There you go. Go.
Hi, everyone. I'm Raphael.
I'm Alan.
And
I'm Slossie.
we're going to talk about control flow attestation and embedded systems. We're going to first start with some background. In our technology populated world, we are surrounded by IoT devices, and it's expected to only go higher. So this will inevitably result in some security problems once they get more and more into our life. But why is this going to happen? Why is this a problem? Don't we have ways to secure our devices already? To understand why this would be a problem, we have to first analyze what embedded systems are. So embedded systems are specifically designed for a task. They are supposed to be simple and they're supposed to be fast. That's why we get to have phones and things that can be deployed. And it's because of that that our current security systems would not work, because our existing security system require a lot of power and computing, energy and computing power, which, based on what I said, embedded systems do not have that, but that's what makes them attractive. So to make them more secure, we would lose what is attractive about them. So as we have discussed in class, there are different ways to secure systems. Not every securing method that we have is complex and brings a lot of overhead. However, one option would be remote attestation. As we learn in class, that's where you go and you read the memory, you see if the code has been corrupted. But as we're learning, and CA4 also talks about this, this is not necessarily the most secure method, because the person could change the code, and when you request for attestation, they could change it back, and then you would not know that something is wrong. So this picture more or less explains what static attestation would look like on an embedded systems. Attacks that are code reuse based would not be detected by simple static attestation. We have also learned that there are other ways. Maybe you don't have to use only static attestation. We can use control flow integrity and control point integrity, as we learned in class. However, poor integration of these things would lead to not so secure devices. Why would it be? Because they don't tell you where things went wrong. They just tell you something went wrong, and that would leave the user with very little information as to what the next step would be, which led us to our control flow attestation, or C-flat. This is a technique that goes with it keeps track of the execution path. So not only is going to tell you something went wrong, but it's going to keep track of what path did you take. That way you can validate whether the path is valid or not, and the user can assess if the system has been compromised or not. One thing that is worth mentioning is that C-flat is specifically for embedded systems. It's not meant to be implemented in larger, more complex systems. And now Celeste is going to explain more about how C-flat works.
So now that we have a little bit of background into C-flat, I'm going to go a little into the system models of how it all works. So there's a lot of different steps involved in C-flat's model. The first step is the verifier, which is not the target device, but something off to the side. right, generates a control flow graph, which is just a graph of all the possible execution paths or possible control paths for a program, and it stores that data offline in a database. And so the graph kind of looks like this. In this example, we have all of the nodes are basic blocks, kind of like what we did in coding assessment 3, and each of them end in a branch instruction. And then all of the edges are node transitions due to those branch instructions. And then one other thing to note is that all the edges are computed using cumulative hashing, which just means that each of the control paths or each transition to a node depends, or the value of the edge, the weight of the edge that connects each of the nodes depends on the hashes before it, essentially. And they used Blake 2 for their cumulative hashing in this example. So this control flow graph is stored in a database on the verifier side. So step 2 is the verifier issues a challenge to the prover, which is the target device that you're trying to attest for. And so the verifier wants the prover to provide its current control flow execution. And so on the prover side, that execution is obtained through a hardware trust anchor, or a hardware trust anchor that's used to compute the authenticator, which is just the cumulative hash of the current execution flow for the program. So for example, this is the overall control flow graph, and then the authenticator is just the cumulative hash at the end of a possible execution path. So next, now that the prover has a notion of the path, it needs to send that report back to the verifier. And so the attestation report is computed over a public key signature, over the challenge, and the authenticator, which is just a cumulative hash. So the prover sends that back to the verifier to check its database and then subsequently verify. So this is kind of like high level, all of the steps that I just described. And we just talked through all of them, so I'm not going to go into it, but I just wanted it there if you want to take a quick look at it. And if you guys have any questions, hopefully this might fill in any gaps that I might have missed in what I was talking about. So now we'll go over to C-flats example cases. Oh, my fault. Yeah, I still had a little bit more. So there were a couple of challenges that they talked about in the paper. A couple of them we talked about a little bit in class. Like last class, we talked about loop handling, right? If you're doing cumulative hashing, every single iteration of a loop is a different hash, and that's a lot to have to keep track of. And so the way that loops are handled in C-flat is that when a loop is entered, that's one cumulative hash, and the number of iterations that loop took is a separate quantity that's also delivered in the attestation report. For break statements, because breaks lead to atypical loop exits, they consider the start point of the loop when doing the hashing for the break statements. And then for call and return matching, because you can end up in the same place in execution from two different locations because of certain function calls in different locations. They index the call and returns, so you have a notion of exactly where the program went to in its execution path. So moving on to the adversary model, right? The adversary is assumed for this paper to be the following, right? No physical attacks. That's a standard assumption when it comes to single prover attestation protocols. And also that the adversary inherently hijacks the execution flow of the program, because that's what C-flat is meant to stop. So things like buffer overflows that we talked about in class, and also return-oriented programming and code reuse. And then there's also a couple of core assumptions that C-flat holds, like, for example, DEP, or data execution prevention, which means that essentially there's not that assumption that the adversary can inject code into the system. So attacks can only work off of code that already exists, right? And also that the trust anchor is can be trusted, so it can't be modified or changed in any way. Yeah, essentially those two, and that attacks are control flow oriented, so not data, not changing like the data that like a pointer points to, but yeah, more control flow oriented things.
For the evaluation, that we have two study cases. One is the sewage pump, the other one is more complex system. For the it's the soldering iron temperature controller. So the syringe pump is an mechanical which can allow dispense and destroying small amount of liquids. They poured the code to Raspberry Pi, and finally there were 332 CMG edges, which included 20 loops. And the syringe pump mainly contact two function, set the quantity to set the amount of liquids, and to move the syringe either withdraw or dispense the liquid. So several exploits were constructed to test the effectiveness of the syringe pump. So one exploit dispense liquid at an unexpected time is introduced control flow that had not been anticipated, leading to a hash measurement deemed illegal and not stored in measurement database. A more subtle attack involved a non-control data attack where exploits were developed that altered the amount of liquid dispensed. However, the verifier could easily to check the loop iteration counter to determine the motor rotated and that will move forward, step forward. So the performance impact on syringe pump of CPAP, C-flats significant vary with the number of control flow transition attested. To put this into concrete terms, consider liquid dispense per hour, which typically range from 0.5 millimeter to 2 millimeter. This noted that there are only a brief span of seconds involved. The distribution of the overhead vary each individual step. Approximately 10% of the overhead, greater overhead for content switching due to the necessary of transitioning to the secure world. So the second study case is a more complex system. It's on soldering iron temperature controller, which evaluated consists of 70,000 instructions and has over 40 loops. So the heart of security is focused on the PID controller, which is a critical component responsible for comparing the current temperature to desired setting and adjust it accordingly. So for the evaluation and the security implications, the C-flat overheads average 237 microsecond per PID iteration, which proves the significant lower operational timescale. So operational impact with an overhead gesture of 0.03% for attesting once per second, the impact to system performance is negligible. This ensures the system functionally remain unaffected by added security measurements. On security success, the C-flat implementation confirms the integrity of the system combination and output maximum of 490 bytes. So it showed the success of C-flats in securing the system without imposing significant data or processing data demands. So in summary, C-Flat's application to the temperature controller is proven can provide robust security with minimal performance impact. So Stan will talk about
Yeah, so now come back to so now I come to the conclusion that let's back to the very beginning of the point. So there is this such problem that runtime attacks exploit return instruction and transfer the control to unexpected load. There are three major cases you can see right there, and it's illustrate and they are illustrated at the graph at the left, and you can see either transfer the control to the middle of the node or to a node that has a no controllable path exists, or there's a valid node, but there's not, but it is not an actual caller. So because of the existing binary attestation cannot declare such attack, so they develop they come up with a solution which is C-Flat and in this paper, and talking about some challenge in the future world of the C-Flat. So challenge includes that now a lot of IoT devices may have already embedded an operation system, but not many of them support the memory protection unit. I mean, memory protection, which is assumed to be the fundament of implementing C-Flat. And also another challenge is we mentioned that C-Flat mainly focus on the control flow attestation. So if they encounter pure data attack, would be issues for that. And some future work including adapting from to instruction set into in the future update, since the instruction set has been commonly used in the modern MCU. And also they expected to add the pro-based runtime attestation as well. That way they can enable C-Flat implemented on a larger program and also enable a real-time interaction between the verifier and the prover. And further discussion on the maybe let's say the C-Flat in the future MCU markets as the markets as the market develop, and it makes so the high performance MCU with a low cost is possible, which enables a necessary hardware fundament to implement C-Flat on IoT devices, and also a new platform called Transform ARM is announced but not released yet at that time, and it can reduce the switching cycle between the secure and not secure world. You can see at the picture right there. If the it can, so the switching cycle normally go up to 3,000 cycles, can be reduced to a few cycles with that new platform. So some interesting question we put it there is kind of out of scope of this paper, but might be interesting to think of it. And that concludes our presentation. And if there's any questions, we'll be answering here.
Here. Questions?
Yeah, what's the like difference between C-Flat and just the regular control flow attestation?
I think the one that we've talked about in class is mostly been around like static attestation, so just verifying the binary set already exists, but not like while the program is running. So it's this one's more like downtime focus.
So you test the control flow itself, that is like which basic blocks have been followed. So it tests that, for example, did you follow this path or that path? What was the difference between each one, and so on and so forth. Remote attestation is just memory attestation, which means that I just check the control, the content of memory statically. I don't care like how the program actually runs. And obviously, if you do something like a return-oriented programming, you may not even inject anything into the program, into the memory, right? You just jump to different parts of your own memory. And control flow attestation can find that. Other questions? Thank you guys, appreciate it. Thanks, Bruce. So So this is the second paper. This one is about
Thank you.
some T, but for, very little systems. So there's no OS here. Let's see how they can, build a T.
Okay, today we are going to talk about this paper, low-cost, trustworthy, extensible network device with a zero software trusted computing base. So for me, it's introduction and the problem statements. So today's network enable us to increasingly connected device into the local network, which will potentially lead to some new security challenges. And also like some kind of code injections, attack, and malwares also will cause some significant threats. And also some research may focus on combine software and hardware together to design security platforms, but it still puts some challenges in practical implementations. So also some like high-end devices like our computer and the network may have well-established security system, but for the low-end network, there are some kind of resources constraint, so they will lack some standard security features. For the question statements, currently there are lots of like infrastructure providers. They can provide service to various nodes. We can see that each node is under control of the infrastructure providers, and those nodes can run some third-party software to customize their functionality. So there will put some challenges with software extensibility to ensure the secure of third-party modules is a challenge in nowadays networking system. And also for this paper, the author provide a centrist innovative approach. They introduce a cost-effective security architecture for low-end devices, and they focus on hardware-based trust, and they can embed it into the device with low overheads. And it has some core security features, such as they have a very usable attack models, which assume that the attacker has full control of software and the network device, and they aim to provide isolated environment for software modules. So for the next part is the design.
Okay, so now we're gonna talk about the design. So the main design challenge is to realize the desired security progress without trusting any software on the nodes. And under the constraints, the nodes are low-end resource constrained devices. Actually, an important first design choice that follows from the source constrained nature of the nodes is limiting cryptographic techniques to symmetric key. So here's the overview with the 7 sections. For the first section, actually the nodes are actually low cost, low power microcontrollers, and in this design, the microcontrollers used is the TI MSP 430. So actually there are many different ways to manage these keys. The first choice is discarded, because for this choice, the compromise of single node master key breaks the security of the entire system. So the options 2 and 3 are both reasonable designs that trade-offs the amount of secure storage and the amount of computation at the IP site. So now I'm going to talk about the memory access control. So memory allocated to modules is divided into these 2 sections, and the memory access control logic in the processor enforces the data in the section. And it's of the module is being executed. And the node and the code in the test section can be executed by jumping to a more well-defined entry point. So here we are with a table that shows the memory access control rules, and it's enforced by the design using the traditional Unix environment. So the module key, these 3 keys, is managed by the hardware of the node, and it can only be used by the software in these 2 ways. The first way is by means of the following processor instruction. The second way is securing link and the local communication. About the secure linking and local communication. So the two key points are shown above, which is the integrity of SM2 has not been compromised. And second is SM2 is correctly protected by the processor. Actually, the second point is more important. And this is the reason why SM1 cannot just verify the integrity of the test section of the SM2 itself. So here's the end-to-end example. And here we have the different keys, including the SM1, and we have the S. So the nodes right here is like we will talk about, which is built based on the microcontrollers. Okay, so finally here here's the node with the software module loaded. So basically the design ensures the keys can never leave the protected storage area by only making them available to the software in indirect ways through the new processor instructions. All right, so now let's talk about the part 3.
Let's talk about the FPGA implementation of the Senkers. So firstly, it consists of the hardware support for all security features that mentioned before, and as well as a compiler for creating software modules deployed on the hardware. So firstly, we start with the processor. For the processor, they extend the Open MSP 430 to run Senkers. The process focuses on isolating software modules and supporting authentication and secure communication. The isolation part of the processor that enforce access rights to ensure that modules do not interfere with each other. In detail, they use a memory access logic circuit checks access rights, and a special hardware circuit manage these checks across all modules. In addition, they utilize 2 cryptographic features for secure communication. The first one is a MAC algorithm. The research use HMAC, which we have learned in the lecture 3. It's a MAC based on hash. And the other one is a key derivation function. They choose HKDF because it has the similar process with the HMAC and with a spongent as a hash function. And they make some modifications on the MST 430 core. The mini modification is they add new instructions to the instruction set to support Senkers features. And for the next step, they developed a C compiler based on LLVM that targets can compile standard C modules to Senkers protected software modules. It is a creation of secure isolated modules with automatic instrumentation. The detailed compiler features include the in-trial point management and stack protection and exiting modules leadership prevention. Finally, they also develop software stack support the dynamic loading of software modules. They use the ELF files and a customer loader. And for the next step, we'll talk about the evaluation of the FPGA implementation.
So for the evaluation, the paper focused on 4 topics: the performance, area, power, and security. For the performance, despite of during the certain operation, the hardware modification enhancing the security don't affect the critical path of the processor, maintaining the same operational frequency. And for the area, each protected modules add additional overhead, suggested that dynamic keys calculation and using smaller keys for less secure application to improve the size, to improve the area. And for the power, the predicted power increase didn't materialize in experimental data, showing no significant difference compared to an unmodified processor. And for security, Senkers ensure module isolation but can't prevent all vulnerabilities. It secures communication with MACs, preventing unauthorized access. And in conclusion, the paper presents Senkus, a new security architecture for a network embedded device, offering strong security with minimal trust computer based. By tackling isolation challenges in device, Senkus provide a promising a solution to enhance security without significant performance overhead. And we want to end this presentation to discuss the potential for future work. Senkus can involve exploring new cryptographic technology, hardware protection, and integration with emerging security standards. For example, incorporating quantum to Senkus against quantum computing threats. And also, we can tracking efforts to commercialize Senkus-based solution and gather insight from industry partners through case study or interview can provide a valuable information on its practical impact and adoption in real-world applications. Thank you.
Great, thanks. Questions?
So you said they were able to run this on or you said it was on a microcontroller? Or using Unix? I didn't know like you could.
No, there was no Unix. It was just an open MSP.
Oh,
Yeah. MSP 430, like the smaller microcontroller.
yeah.
They run it actually on an FPGA because they changed the hardware, right? So it's eventually becomes.
Yeah.
Yeah, so I mean, eventually the idea is that you can manufacture this as just a microcontroller like that.
How will they ensure in this period that this be not manufactured by them? So how will they ensure that if they are reading the keys, they will not take from the protected area by the software?
Well, I mean, these are all implemented in the FPGA, so they assume that they have full control over the hardware. So they put the keys, for example, inside when they were designing. The idea is that once this becomes, as your classmates were saying, that once this becomes actually manufactured with industry, then they put the keys inside the protected areas anyway. Does that make sense?
But even if software which is able to access them, how will it prevent the software from accessing it? I mean, we're communicating.
Oh, so that's all the self-checking thing, right? So like only the code sections that's supposed to access the key can access the key. So they can protect that by checking the PC. So essentially, if any other part of the code trying to access that particular reserved area, it will be blocked. Hardware will block. All right, thank you guys. Appreciate it. That's true. So last but not the least, we're going to talk about Pistis. This is also another trusted execution environments on open MSPs.
Okay, so hi everyone. So this is our group presentation on Pistis, which is a trusted computing architecture for low-end embedded systems. And I'm Tianyi, this is Yilun, and this is Xiaoman. So the problem that we are facing and Pistis is trying to solve is still like cyber attacks that's targeting IoT devices. And one example is memory botnet, which I believe some of our classmates have talked about in previous presentations. But for like low-end devices, or in another word, like commercial off-the-shelf microcontroller units, this problem is much more severe. And because these these low-end devices, they often lack the hardware, such as memory protection units, and their software often runs bare metal without operating system support. And these low-end devices, like their keys, often relies on remote attestation and with many assumptions, such as like silent adversary or like optimal code or one-hop communication, etc. And in their case, hardware-assisted RA mechanisms are not ideal due to like flexibility and cost and compatibility issues. And what Pistis proposes is a pure software solution. That's is actually one of the first software-based solution that offers memory isolation, remote attestation, and secure code update service at the same time. And their secure update service is targeting von Neumann architecture. And they are basically using software to isolate memory and to allow like RA and other secure updates like services. And below we can see a table that shows what Pistis is good at, or is like its main advantages versus some other popular and existing security architectures.
All right, so how does PTS achieve security without any hardware feature? Let's look at it. So firstly, here is the paper's logic. Firstly, there is a TCM called a Trusted Computing Module, and Pistis initially deploys it as the initial code. And later, Pistis offers some security services. The two main services include remote attestation and secure code update. And later, we need to validate it, and it's called formalization. So we need to verify the design's correctness and implementation for strong security guarantees. So how does CEM is implemented, and how does it achieve memory isolation? So TCM is responsible for enforcing memory isolation and protecting sensitive data and code from the unauthorized access. And memory isolation is very useful because only trusted code within the TCM can access and modify our critical data. There are 4 features for TCM and memory isolation. The first is the initial code. It acts as a bootloader, so you need to decide whether to boot from the TCM, the trusted memory, or the untrusted memory. And the second feature is loader or verifier. So loaders need to receive the untrusted software or the untrusted code, and you need to verify whether it is Pistis compliant, which means whether it is secure or unsecure. And later is virtualized instructions. If we found that the codes or the blocks of memory is unsecure, so we need to replace them with the virtualized instructions, which are a set of functions that represent the safe equivalent versions. We also need some helper modules, which are other necessary helper functions, such as the ones that read and write memory pages. And here comes the implementation and evaluation methodology based on MSP 430 MCU. So the authors make a few assumptions that the application is composed of sequences and combinations of primitive instructions. They make 13 of these applications and they set their own primitive instructions. After they input into the system, so the first step is to distinguish between different memories. The memories are divided into 2 parts. The first is persistent memory, and the second is volatile memory. They also need to record the starting point and the ending point of each memory and to recall what they are used for. And the second step is based on the access policy, which is called AP. So the system needs to decide whether this block of memory satisfies its AP, which is access policy, which means it is secure or unsecure. And of course, if it's not secure, we need to replace the unsecured block of memory or block of codes with the secured version, which are called virtualized instructions. We talked about it before. And the authors also post some evaluation metrics, such as memory footprint, execution time, deployment time, and power consumption. And that's for the methodology. And here comes the next person.
Oh, yeah. So I'm going to talk about the potential future works. So as you can see from this picture, so there are several main secure services that the PCs can provide. So the first one is the memory isolation design, which is talked very specifically earlier. And in this article, it is the architecture and all the correctness is fully verified. So it is very reliable. But for the other secure services, such as remote attestation, secure code updates, key management, and access control. So the architecture and the implementation of them still needs to be verified. So that's what we need to do in the future, that we can do in the future. So as mentioned by the article, there are other things that other than the PCs that we can design and implement. So one of the most important things is the control flow attestations, which is CFA scheme. So this is the CFA. So in June 2023, Antonia, as we can see from this picture, Antonia proposed the interrupt safe control flow attestation, which is the ISC FLAT on the IEEE RTAS. So the benefit of this one is that it is compatible with the existing MCUs. So it's very easy to use. So as you can see from this picture, the solid arrow is the value control flow transfers, and the dashed arrow is the path taken during the particular execution. So this is the when you come to this is a lot of noise here, and when you give it an execution, and you can get two results. So we can come with a valid path and an invalid path. So we can see that from here, this is an invalid path. So as you can, in September 2023, Matthias proposed the guaranteed TE on the IE cloud. So by using the two ETEs, it prevents both the cloud providers from extracting critical data and modifying the important data, and also the users from the influencing the CFA results. So as you can see from this picture, there's two TEs, so they won't affect each other. So this is much more secure based on the cloud. So here are some discussion points that we can discuss. So the first one is can PIS internalize engineering models that can provide a reliable computing resources for services like AWS, GCP, and Azure. So here's the reference article that you can read after class. So it is called the PIS composing AWS spot instances with guarantees. So this is about the utilize the PIS in the AWS services. And the second discussion is under what conditions should we use PIS, and what is the working mechanism of it? So I have already seen this in the PowerPoint that in the lectures that maybe the professor can cover, but here are some, because just like using the MCUs and the TEs and something just a software-based approach, and this is all the conditions that it can be used. And the third discussion point is that what can we do to improve the performance? Just like we have discussion earlier, the evaluation, just like the memory footprint and the runtime overhead, and reduce the power consumption of the PCs. Okay, so that's all for our presentation.
All right, cool. Any comments, questions? Yeah.
Could you go back to slide, the evaluation? What is AP on S2?
It's access policy, like it need to, if a block of memory satisfies access policy, it means you can understand as it's kind of secure. Yes.
Yeah, so think about it, there are a bunch of different applications here, right? And then each one wants to access their own app. So what this part does is checking whether they are supposed to access that part of the memory. There is some form of access policy that says that this region is for application 1, this region is for application 2. And then you check that dynamic.
And then what does replacement, like if not replacement mean, does that mean you like offload the program, like just before it, or what does replacement mean?
If it is secure, we can just use them, but if it's not, we need to replace the instructions with the virtualized instructions, which are secure.
So this is during the compile, I believe this S3 of yours is during the compile time, so they actually recompile the code with those checks. And then during the actual runtime, then if somebody tries to access something that they're not supposed to, then there are various things you can do. Most of the time, you just do it with some form of like, you create some errors or you run some other instructions such that you don't really provide the data to the other application, but just let it continue without really interrupting the system.
Right, but so the process is if you check that it violates the access policy, you'll stop it from running and then go recompile and then let it run again.
No. So there are two phases. One is that during the compile phase, you make these checks, and then you replace some instructions with some other instructions. So for example, calls has to be secure calls and all those things. During the runtime, you just check whether you have those accesses. If you don't have those accesses, then again, there could be either like you create an interrupt, you like notify the user, or you just continue without really servicing that particular instruction.
Actually,
Yeah,
This software only solution, right? So this was software only solution. right?
it's software only
So
solution, yes.
it's using hardware and like it's having a read only memory kind of structure that.
Yes.
So how is it different from the normal, whatever we discussed in class?
What we discussed in the class mostly has some level of operating system that kind of handles this. So this blue part is really kind of that operating system that we discussed in the class. But here is like very, very simple, right? Like it's just doing some bare minimum functionality like remote attestation, some level of isolation. All right, thank you guys. Appreciate it. All right, let's have a quick break and then we'll come back and talk about those other things. So, few things. One is, actually, let me stop share. One is, exams next week. It's going to be in person here, right? So you have to be here. If you actually go to the website, you will see that I put some samples. There are 2 samples for last year. So the exam looks, oops, I'm not sharing it all, sorry. Finally, all right. So the exam looks like something like this. Usually I have 2 parts. One is like a short questions or true or false questions. And then there is like, there is a free answer question part. Okay. The free answer question parts, like, I give you something, I ask you like how this works. So for example, like describe how differential power analysis works based on this figure, and you have to kind of write down stuff. And then the true or false questions are basically based on what we discussed in the class of like, what is, let me see, where is the true or false questions? Oh, I think I didn't have true or false question for this. For this part, but yeah, sometimes I also have true or false questions for various different things. So you should expect seeing something like this, that a bunch of different short answer questions, some that are more kind of elaborate questions, and so on. One thing to keep in mind when you're seeing the samples is the samples are for a different year, right? So the syllabus is slightly different. So there might be questions that you never, like, there are topics that we didn't discuss this year. So it's slightly different than what we've seen this year. So just don't be surprised if you see that, for example, something you haven't seen before. And then let me see. This is the second sample question. Oh, this one has true or false questions. So yeah, things like, stream ciphers can achieve perfect secrecy, true or false. CAM is not vulnerable to quantum attacks. Hash are usually 2 times faster than max, things like that. And then, by the way, the exam will be open book, open note, open laptop. So you feel free to bring whatever you want during the exam. Usually it would be probably around 1 hour to 1 hour 30 minutes. So it would be entire class on Wednesday next week. And yeah, this is there, just take a look at them, let me know if you have any questions. It would include everything that we discussed in the class, right? And not the papers itself, but like everything else. Any questions?
How will the format of the exam be? Will it be like a grade scope form?
Yeah, will be grade scope, so you have to sign in on your grade scope and answer it, so bring a laptop for sure.
Right, and that the intro slide mentioned it open notes. Is it also like open search or not?
Yeah, you can search as well.
So we can Google.
You can Google, yeah. So you can do whatever you want on your computer, except chatting with other people. Other questions? In the past, I mean, this classroom, I didn't have this issue before, but just be careful that there might be Wi-Fi connectivity issues, just because, you know, there are more people in the room. This doesn't work, unfortunately, for many, especially those who has older version of Mac. So my suggestion is to be prepared, at least download most of the things you think you will need, right? Like lectures, books, I don't know, whatever you think you might need, try to download them and have them offline. And then searching, of course, you need an internet for it. If it works, then great, you can search. If it doesn't work, then at least you have your files offline, okay? We cannot do anything if it, you know, the Wi-Fi doesn't work, it doesn't work, okay? So don't expect, we don't change any sort of like the format of the exam because of that. Other questions about the exam?
Will there be questions from the readings, specific stuff like that?
No, not readings. I mean, paper presentations, but mainly kind of like high level idea of paper presentations. So make sure to watch the videos, both the lectures and paper presentations, to just get some basic idea of, like, for example, I don't know how PISTIS works. The second thing I want you to mention is make sure to submit the course evaluation. I already posted on Campus Wire. I think it hasn't started yet, right? Or it does, no, yeah. But once it starts, please go and submit your course evaluations. It's very important for me because I always read this very, very carefully and based on kind of the feedback and suggestions and make changes. So comment on things such as, like, you know, did you like the modules, which modules you want more details, less details, what other things you want to see. Comment on the computer assignments, you know, both at the just general about how do you feel about computer assignments, and then if there are like specific things that you like to be changed, particular ones on all of them, let us know. And then of course about paper presentations, paper readings, and all those things. So yeah, comment about all or some of the you know, different components of the class so that we can use it for future. I'm gonna add bonus points if you have, you know, good participation. If you have 75% participation, I'm gonna add, I think I said 3% to your exam. And if you have more than 90, I'm gonna add 5% to your exam. Okay, just
75% of the class participants?
Yes.
Oh, okay.
Yeah. Any questions about that? Cool. So, and then as I said, next week Monday would be reviewing the concepts that we you know, talked about. I think based on your feedbacks, you want to see a little bit of blockchain, my research, a little bit of crypto. Anything else anybody wants to add? Okay, so I'll add those things to the presentations as well. Let me just finish the things that we discussed last time, and then I'm gonna let you guys go. Actually, it's faster to do it this way. All right, so if you remember, we said that essentially teas in general, they have these different flavors, right? So depending on whether you have operating system or not, what you want to protect, whether you have multi-tenancy, what sort of hardware resources do we have? Do we want to kind of, like, you know, add IO to the system or not. And then you have seen some examples, right? So for example, you saw Pistis. The idea of Pistis was, let's look at system that doesn't have any sort of operating system, doesn't have any hardware support, can we still achieve some form of, trusted execution environment? They're kind of like trying to say that, okay, this is kind of the gap that they're trying to fill, which is, security guarantees on the y-axis, and then the amount of resources that you have on the x-axis, and you want to use it as minimal as possible on the hardware side while achieving as much as possible on the guarantee side. Okay, so they do these various different things, and kind of the idea of this was essentially adding this layer of memory protection into the system and providing services such as remote attestation, secure core update, and some form of a runtime library. And then the kind of untrusted part of the system still remains. Like you have a bunch of different applications, you might have malware and all those things. And then another important things about Pistis was that they also had this offline phase, which they have this tool chain where essentially an untrusted source file is kind of compiled into something that is compatible with this kind of runtime library. That was their idea. And then essentially this is kind of like, how the system works. Think about this is that you have a memory, and then you can divide this memory into the trusted part and untrusted part. And then within this trusted part, then you have these different capabilities such as runtime attestation, secure core update, and so on. And then in the volatile memory, they can also have protected code. Everything here is based on this fact that you can indeed protect your code, and this code cannot be writable. Okay. And if anybody wants to read them, they only needs to be able to read them from particular entry points. So they cannot really run arbitrary code on this side of the system. There should be specific entry points, which is usually the beginning of different functions in the system. And then as I said, there is an offline phase to it as well, which essentially what they do is that if you have different codes like this, okay, they will if you have code like this, that you have this unsafe jumps that call R10, which is R10 could be any value. So this could be potentially attacked, given that, you can change R10 to any arbitrary value. So in other words, you can jump to any part of the program. They change this into kind of these type of safe calls. That's, they put this into some registers, and then they have this what they call virtual calls, which essentially make sure that we only jump to the part of the memory that's when that register is safe. What is safe and what is not safe, they have detailed implementation and description of that. But generally, this is kind of how you translate your code into a safe code that is compatible with something like Pistis. So essentially, you recompile your code to follow a specific format, and then during the runtime, you kind of provide runtime libraries to kind of follow that format. That's kind of the basic idea. Okay, and of course, this will result into huge performance overheads, because now what used to be, for example, one instruction or two instructions are now many instructions. So two things will happen. Your memory footprint will grow because now you're adding more code, right? So obviously you will see that your code size grows, and this is around 41%-ish. And then another bigger thing is that your runtime will grow, because now you need to run more instructions, and of course this will result into a slower time, the same thing. But what you gain is that you don't add any hardware to your system, and you still achieve some security guarantee. So this is kind of the trade-off between security and performance overheads in the system. Okay. Yeah, so this is Pistis. Another one that I want to talk about is this Keystone. So this is actually an open source key for RISC-V designs. You can actually play with it if you want to. So the idea of pistis is that again, similar to all these different thread models and keys, the idea is that you have a bunch of sensitive apps and some other apps. You want to have a protected area for the sensitive apps. You want to ensure confidentiality and integrity of those sensitive apps, right? So how do they achieve that? You use, they use this, T's, and their goal was, like, as I said, reducing the trusted computing base, or TCB. And then they compare themselves with things like SCV and SGX and Trust Zone. What they're trying to achieve is that they're trying to minimize the amount of, trusted code base in order to achieve these things, because their idea is that, like, they want to kind of use this keystone in embedded system domain, which is kind of like usually limited in terms of memory size and so on and so forth. So what they said is that you can actually have kind of more flexible design decisions. Remember, like we talked about Q and say that, okay, you can add runtime, you can have user space enclave, you can have kernel space enclaves. So these guys kind of follow the same format, as in, like, you can now choose how much memory you want to assign to your T, whether you want to have a bigger kernel or a smaller kernel, and so on and so forth. So it's kind of very customizable in the sense that you can decide how much, what is assigned to what, so that based on the needs of the user, you can actually design your system. And then another interesting thing about, as I said, Keystone is that it's based on RISC-V, so everything is open source, so you can actually design this in your own way, versus neither of these, Trust Zone, SGX, or SCV, none of them are actually open source. So these are kind of like the main things that they have, minimal TCB, modular extension, fine-grained configurations, and so on and so forth. So how do they actually do this? For RISC-V, there are, if you remember again, that we had, like, user level and system or privilege level, which was the operating system. What you need to have is like this additional machine level, such that, that's where your security machine kind of operates. And again, this is where this SM or security monitor sits, right? So you have a bunch of different enclave apps. They might have their own runtime, and then everything is basically, kind of managed and controlled by this security machine. And this is at what they call M mode. So RISC-V has basically 3 different modes: the user mode or U mode, the supervisor mode or S mode, and the machine mode or M mode. So it supports these different various ways. And of course, underneath is the trusted hardware. We always assume that the hardware is trusted. We build the hardware correctly, so we can trust it. So yeah. So, and then if you remember, I told you about this PMPs, right? So the idea of PMP is to make sure that any application that's supposed to access a particular part of the memory, they can, okay? So blue means, for example, they can access it, and red means that they cannot access it. So the idea here is that, for example, PMP2 says that for enclave 2, this is the part that we can access. For PMP1, this is the part we can access, and so on and so forth. So essentially, this registers allows you to access part of the memory and not access the other part of memory. And as long as you have these physical registers, you can have multiple different enclaves working at the same time. You just need to kind of define, this is the parts that you have access to, this is the part that you don't have access to. Okay. And then, of course, security monitor has access to everything, right? So this is the whole point of a secure monitor. Yeah.
In this one, there is a security monitor. Okay, SM is security.
Yes.
But you cannot access PMP0.
Say it again.
PMP0 cannot access PMP0.
PMP0 cannot access SM. Yeah.
Can access everything.
Security monitor can access everything. So this is security. So PMP7 is the security monitor that can access it. Does that make sense? So for example, for enclave 1, you can see that enclave 1 can only access here. but cannot access these different parts of the memory, including the SM, right? So this is how we create this isolation between these different applications. So what does the runtime do? The runtime provides some minimal services for these applications. The runtime, as I said, stays in the supervisor mode next to the operating system, so it's kind of same level privilege as the operating system. And then what it does is kind of provide interface with the app. You can have bunch of different types of runtimes. The famous one is what's called Cell 4. If you're actually interested, take a look at what is a Cell 4. This is kind of like a very small kernel that's being able to do various different things. So, examples of things that the runtime does is things such as, assigning and freeing memory, handling the pages and page tables, interacting with the I/O, providing system calls, libc libraries such as like printing and scanning and all those libc libraries that you have. Okay, so these are the things that you probably expect from a runtime library. Okay, and then you can, again, the main thing about runtime libraries is that you want to make them as small as possible because this is part of your trusted computing base. If you add more things, then essentially you will have a full-fledged operating system. But the problem with that is that it becomes more and more difficult to kind of make sure that it's not buggy. Okay, so you want to have a minimal amount of things within your runtime. Okay. And then the memory management, as I said, so essentially, so this is kind of like the model that Keystone has, that operating system and the runtimes have a completely different types of memory management, right? So the pages and page tables and everything stores within the runtime. So the runtime actually handles all the memory accesses. The good thing about this is that it no longer needs to switch back and forth between normal and secure, which kind of saves a lot of time. Also means that if the system is compromised, this part stays safe. All right. So this is another important things that you need to achieve. Various different memory mechanisms you can have. You can do this for your VRAM. You can do this for your cache as well, in order to protect your system against various different things, including, for example, cache side channels that we didn't really discuss in this class, but but this is kind of like the baseline. Everything is shared, right? Like, cache and your DRAM, everything is shared, but you can actually have this various different methods in order to make sure that your system is indeed secure. You can isolate things. You can, like, for example, partition your cache such that only, for example, unique or a specific part of your cache can have access to your, for example, SM, your enclave. For example, this figure here shows that you can actually say that, okay, only half of the cache, for example, can house things for the SM or for the enclave. The good thing about this is that there is no sharing between non-secure applications and sharing secure applications even in the cache. The problem with that obviously would be lower utilization, lower, lower latency, higher latency, and but worse performance. You can even add encryption. So, for example, let's say if you're really worried about if someone like probing your memory, right? So what you can do is that then whatever like leaves your cache and goes to your memory can be encrypted. So additionally, you can have hardware encryption or even software encryption, depending on what sort of threat model you're adding to your system. And again, these are the decisions that you can make. And each one has its own trade-off. So for example, if I don't partition, then I'm vulnerable to cache side channel attacks. Okay. If I do partition, then that's great. Then I'm safe against cache side channel attacks. But the problem is that I'm going to have lower performance. Then if I want to kind of be secure against hardware attacks, I need some form of encryption. So this encryption could be hardware, could be software, but again, there are trade-offs when we are doing this. So ultimately, you can have something like this that satisfy all the requirements. So protect your software, protect your cache side channel, protect your hardware. But this would be very expensive in terms of hardware support because you need to add all these things. And of course, the performance may not be as great as what you would have in a baseline system. Make sense? Questions? All right. So they have a bunch of different evaluations. If you're interested, take a look. This is kind of like, the runtime overhead, as you can see. So we are talking about like, somewhere between 3% to 7% overhead in terms of runtime when we are running these different applications, okay? The cost of memory protection is also depending on whether you have cache partitioning, whether you have software encryption and hardware encryption or not. This is kind of the percentage that you can see for various these are different applications. This is the amount of overhead you will see when you have all these different things. If you're interested, definitely take a look at the paper, but these are different numbers depending on what we have on the system. All right. So if you're interested, take a look at this keystoneenclave.org. They have very nice lots of details about tutorials about their code, how you can run it. So I mean, those of you who are a little bit more enthusiastic about this, definitely go and take a look about this. Okay. I guess that's it with what we have. So just a quick reminder: we did status checking, we did control flow integrity, and then we do isolation. The isolation came from T's, right? So then this level of isolation could be at various different layers. And then there are trade-offs when we are doing this. In order to kind of check the integrity of control flow, what we did was doing control flow attestation, which, your classmates discussed. And then for dynamic status checking, we do runtime remote attestation, which you seen last week and in your project. So these together basically will give us kind of runtime or protection against different memory corruption. So here, all of these cases, the assumption is that we need to live with memory corruption, right? So of course, another solution for this is completely fixing the issue of memory corruption by using memory safe languages, by removing, buggy software and all those things, which we have to do it in parallel with all these things. The problem is that there are lots of legacy software that we cannot really change. So we have to live with them. So that's why we kind of like doing these different solutions to kind of live with those. Okay, so this kind of like two-pronged approach where we fix memory safety at the same time we're trying to kind of live with memory safety. Okay, cool. Let me see. So this is just a C flat that's they're discussed. Yeah, that's pretty much it. Is there any final questions? How we're doing with time? Okay. Any final questions? Good. All right. So see you on Monday with the reviews.